Okay, hi everyone. I think we can get started. Welcome to the afternoon session. Our first speaker is Brice Williams.
Hello. As Maria said, my name is Brice Williams. I'm from Washington State University, and I would like to discuss multi-messenger astronomy with massive binary black holes and LISA. As we've all heard this week, the importance of why MMA with LISA and massive black hole binaries, but I'd like to reiterate a couple of those topics. LISA will help confirm the existence of binaries in AGN, which is otherwise difficult to ascertain, and from being able to detect these sources, we'll have a better understanding of the roles of mergers in galaxy evolution. We'll be able to put tighter constraints on cosmology, from the luminosity distances we see from LISA gravitational waves, as well as the electromagnetic host redshift. We'll also be able to understand what powers the AGN variability. So since LISA will be able to see the black hole masses and again we'll be able to observe the bolometric luminosities, we can build better test models for gas accretion, disk structure, spin evolutions within these galactic nuclei. We'll even be able to dive into some tests of GR and how to discern the environmental effects of these galactic nuclei from possible deviations of GR. The most interesting part of this to me is building that full story of black hole evolution. So how do we get from the stellar-sized mass black holes that we see with LIGO all the way up to the supermassive black holes that we see at the center of galaxies? What's nice about LISA is that it'll be able to see these intermediate mass black holes, and with MMA we'll be able to understand the environments that they exist in. So if we see that these intermediate mass black holes are merging to produce these supermassive black holes that help fill in the gap of these black hole evolutionary story. So the electromagnetic observatories that I'll be discussing today in this talk are the Legacy Survey of Space and Time from Rubin, the Roman High Latitude Time Domain Survey, and New Athena. So LSST observing in the optical range will cover the southern celestial hemisphere, and will have an absolute magnitude of about 24.5. Now, because LSST will visit multiple sky locations multiple times, you can actually co-add these signals together to see slightly higher magnitude limit of 26.9. So you can see fainter sources. Roman, operating in the near infrared, will be able to see, upon the estimates of performance, magnitude limit of 28. Again, you'll be able to co-add these sources for repeated observations to be slightly higher than that. But again, the sky coverage isn't as great as LSST. But we'll still be able to see about 18 square degrees for the wide imaging and 6.5 square degrees for the deep imaging. Roman being scheduled to launch, I think initially at August 20th, that might be pushed back to August 30th now, but still in a couple months, Roman should be heading its way up. And then lastly, New Athena, which will cover the X-ray spectrum, seeing a luminosity limit of 10 to the 41 ergs per second. Don't quite have the sky coverage, ideally the whole sky, but being launched in 2037 after LISA allows it to be useful for sources of opportunity. So being able to switch to the sky location that we understand that a binary exists in earlier in its in-spiral to try to capture an electromagnetic signature of the merger happening. Versus Rubin and Roman probably ending their mission lifetime before LISA launches. We'll have archival data that we can dig through to find the potential host galaxies of these binary mergers. So for this to be possible, we need to be able to see these sources in all observatories, right? In LISA, in our electromagnetic spectrums, observatories. And so what we did is we plotted the threshold for these masses at what distances they'd be able to see in LSST. So here we have, in the gray curve, LSST distance and mass threshold for, based on the bolometric luminosity and the Eddington fraction. So the solid line is an Eddington ratio of 1, 0.1 for the dash, and 0.01 for the dotted. And anything below those curves would be able to be seen by LSST. So you can see quite far if you have an ideal situation with an Eddington ratio of 1. But of course, we don't exist in that that realm. Probably see things much less, so around the dashed or dotted line, but still see pretty far for the massive black hole binaries that we think we'll be able to produce. And now we want to know what LISA sources inhabit this threshold. And so what we did is we took optimistic located binary source within the ecliptic plane and face on, so the inclination of 0, and we took the last year prior to merger all the way down to its innermost stable circular orbit and calculated the SNR. And what we found is that the SNR for LISA sources at these thresholds is still very loud. Okay, right here in purple I have plotted an SNR of 400. So they'll still be able to have nice constraints and detectable sources that inhabit both the EM range and also the gravitational wave range. Folding in these other observatories, now with New Athena and Roman, we'll be able to see a little bit farther, or a lot farther for New Athena. The range of SNR is still very high for LISA sources, so we still show that the limit of New Athena is still slightly above a LISA SNR of 300. So anything below these curves it will be able to be detected, and what we found is that at the higher mass range will be limited by LISA, but will be limited more by the electromagnetic observatories for the lower mass of these massive black hole binaries. Because we took the last year prior to a merger for the sources, we ended up using the orbit average antenna response function. But because LISA is moving in time, that creates patterns in the sky that are more sensitive to others. And so here we plotted in red the parts of the sky according to the orbit averaged version, which parts would be more sensitive than others. So you see in the ecliptic plane you have 4 spots of red, and then along the ecliptic poles you have the white spots. And although there is some variability, that variability order is only about 20%. So for loud sources, you still won't see much less than what we showed earlier in the 400 or 300 range. So we grayed out the galactic plane here, just because we want to see farther than that, outside of that. And then also anything that's not within LSST sky coverage, we have faded in the northern hemisphere. So hopefully this creates where we can focus our time to try to catch some of these MMA sources. Now, because the antenna pattern is changing in time, we'll have parts that are more sensitive than others. We'll also have parts of the sky that will have tighter constraints on the localization. But already for high SNR sources that we know that localization will be very good. This is just one example of the many different works that have been done to show how well LISA sky localization will be constrained. So just to build on our story, is that the sky localization will be well within the field of view of LSST or New Athena to help limit the number of sources that are potential host candidates for these binaries. But with the caveat that there will still be hundreds of sources within LISA's sky localization, we would need other ways to determine which is the actual host. One of these ways is through the luminosity distance. Luminosity distance, again, for high SNR sources will be well constrained. So we can eliminate some of the EM host galaxies just purely based on the distance that they inhabit. Another way to help limit the number of sources and hopefully find the accurate one that contains these binaries would be looking at the variability in the EM signatures. If these EM signatures also have the variability on the frequency scales that the binary is orbiting, then that could also hint at the potential host galaxy to help build that story and with the more accurate, build a more accurate story on where these binaries exist and the environments that help create them. So to wrap up, I'll leave you with this, that our best prospects for AGN MMA with LISA and LSST inhabit the 3.2 times 10 to the 4th to 1.3 times 10 to the 6th solar mass binaries. Because LISA will see much further than all of our electromagnetic observatories, the sources at the threshold of the electromagnetic observatories will still have high SNR in LISA, thus helping us minimize the errors in sky localization and distances. And then also, because LISA is moving in space, we'll have some variability in the sky localization parameters just purely based on its orientation and when that source comes in. But the variance for an optimal source is only on the order of 20%, so still hopes are high. And with that, I'll take any questions.
Questions?
That was great. I don't know the answer to this because I haven't done the calculation, and you're going to get it because you're the first person. So, we focus a lot on finding the LISA counterpart or the, 5 years from now, LISA precursor. But something I don't know is if we were talking about something that's going to merge 100 years from now or 50 years from now after LISA, what's our detection capabilities with these kinds of surveys? Are there signals to be seen? Because that sort of stuff will inform population and science we extract from LISA and everything, even if it's not a counterpart to an actual source.
Right.
Yeah.
The short answer is I don't know.
Okay, good. That's why I asked. Okay.
But yeah, what you hinted at is right. We can still, I guess, backward or forward evolve these sources to suggest what we will see.
Yeah.
Environments that they inhabit. So if we have, with these new electromagnetic observatories, have better understanding of the environments involved at the galactic nuclei, then of course we can run simulations and throw in, binary sources to see what those gravitational waves would look like. And thank you.
That was a lovely talk. Thank you. I was just wondering why you're excluding the merger part in the SNR for LISA and maybe the sky localization too. Just talk me through that.
Why we, of course, thank you for the question. Short answer is to make the math easier. Evolving down to just the innermost stable orbit, just to make the math easier.
Any more questions? Okay, let's thank Brice again.
Thank you.
Sorry for the technical challenges. The next talk is by John Gair.
Okay, thank you. So I'm going to be talking about how to do population inference with LISA. This is work that's based on a paper that appeared on the archive in January with Alex Tubiana. This talk was originally scheduled to be in the data analysis section. It was moved here because I won't be here tomorrow afternoon. But it should still be relevant for people in this room who are interested in doing population inference with LISA observations. I should also mention that there are a couple of other works that are ongoing, one led by Alex Criswell. There's already a paper in the archive from that, and then there's another effort by the group in Zurich, Ariana Renzini and collaborators, called Heebie-Jeebie, and she gave a talk about that on Tuesday. We've gone about this work starting from a different philosophical standpoint, but there's been a lot of convergent evolution in the features that we've had to include in order to make progress. Okay, that does not work. So what do we mean by population inference? As you heard about in Tyson's talk yesterday, and I'm sure many of you knew beforehand, the way we typically do parameter estimation in the LISA context is using Bayesian techniques. So we start with some prior information on the parameters of our source. We then go and collect some data, which is described by the likelihood, which is a property of our instrument, and that allows us to update the prior information to give a posterior on the parameters. So the difference in population inference is that we now introduce extra hyperparameters into our prior that characterize the population as a whole. And then we assume that these population level parameters are common across events, and we constrain them by writing down a joint likelihood for all of our events, marginalizing out the individual event parameters, and then constructing a posterior on the population level parameters. And that's what's written in this bottom.
Your slides are not advanced.
Okay. So where was I? Okay, yes, hierarchical Bayesian inference. So by combining observations of multiple events, we learn about the population level parameters. This is what is commonly used in the analysis of data from ground-based detectors, and the typical formalism for this is written down here, which is what I described, with this addition of a selection effect correction that arises because LIGO doesn't use all of its data. There is an initial search phase in which we identify interesting segments of data that might contain signals, and it's only those that are then used in the subsequent analysis. And so you need to correct for that when you're doing the population inference. So the way in which this is done in practice in the LVK context is primarily through per event reweighting. So you first do an analysis in which you construct a posterior on the parameters of each individual event using some fixed reference parameter estimation prior, and then to do the hierarchical inference to get your population parameters, you reweight those samples in your hierarchical inference stage. Now, in this project, Alex and I set out to try and understand how you would do something akin to this in the LISA context. And so we were interested in saying that if the DDPC has produced a catalogue, what information should that catalogue contain to allow people to just take those results and do population inference without having to redo a global fit. Now, this is not the only way you can go about it. You can also simultaneously constrain the parameters of the population and the parameters of individual events. You can do a joint fit in a higher dimensional space. This is the approach that's being taken by Alex Criswell and Heebie-Jeebie, and that has merits, but it makes it more difficult to then redo the analysis for different populations, and so you need to redo the global fit every time. A third thing that has been done in the context of ground-based detectors is reweighting at the population level. So you take your posterior on the population parameters and convert those into posteriors on different population models. That's something that we should certainly explore for LISA as well, but it only works if the population model you fit in the first place is flexible enough to contain every other model that you might want to reweight to. And so there's a cost associated with that, which we need to understand. Okay, so what are the key differences in population inference for LISA? One, there are three of them. The first is that we don't subselect data, so there is no selection in the way that there is in the ground-based detector context. We use all of the data that comes out of our detector, and that's because we have sources that are present in all of that data. We also don't analyze one source at a time. We can't isolate a single source. We do a global fit, as Tyson very nicely explained yesterday, to all of the sources, and there are no numbers simultaneously. And then the final key difference is that we don't have any off-source data, so we can't estimate our noise. This is typically done in the ground-based context. You take data in the vicinity of a source and use that to characterize the PSD of the noise at the time of the event, and that is then fixed, usually for subsequent sampling. Whereas in the LISA case, we will not have off-source data, so we will be fitting a model for our noise, also as Tyson explained yesterday. So the model we fit looks something like this. We have a model for our noise that depends on some parameters, and then the likelihood is just that model evaluated on our residual. The residual is the data minus a sum over all of the individual sources that are present. So in principle, this sum is over every single source in the data. But we have 10 million white dwarf binaries in the data, and if we tried to marginalize over 10 million white dwarf binaries, it would be very inefficient because it would be a highly degenerate likelihood surface that we'd have to explore. And so for practical purposes, we place some threshold and we don't try and resolve all of the sources. And so we limit the number that we're resolving, and everything that's left over gets absorbed into our noise model. And so there is a movement of sources back and forth between the resolved population and the background, foreground. Okay, and so the way in which we separate between foreground and resolved sources is a choice that we make as somebody doing the analysis. And different choices, so you can make a different choice of the threshold down to which you resolve particular sources, and that represents a particular approximation to the likelihood. And if you make different choices, you're making different likelihood approximations. But these are all approximations. The only real description of the data is the one in which every single source that's there is individually resolved. So we do this split. You can characterize that with a function that says what fraction of sources are with particular parameters are resolved and what fraction are unresolved. And then all of those unresolved sources add up and contribute to the noise, while all the individual resolved sources contribute separately to your likelihood. And so you get a family of likelihoods that look like this, depending on how you define this separation between background and foreground. So every one of them is an approximation to the true likelihood, and so it will be better in practice if this is data-driven. Having set the formalism up in this way, you can easily get results for other population models by doing reweighting in post-processing in the same way that we do for ground-based observations. Okay, so to illustrate this, we considered a simple toy model, a set of monochromatic sources. These were distributed in frequency with a number density that was a declining function of frequency. So we have very many per frequency bin at low frequency and less than one per frequency bin at high frequency. Each source was monochromatic, so it had an amplitude and a random phase, and the amplitude was drawn from a normal distribution that had a characteristic scale which was also a function of frequency. We added Gaussian noise, and the model we used for our background was also Gaussian, and so our total likelihood was d minus the sum over our resolved sources divided by a sum of incidental noise and a contribution from the foreground. And for this resolvability function that specifies how you separate foreground and background, we used a tanh function that looked like this. And so then in practice, what we then did was try making different analysis assumptions, which were characterized by the signal-to-noise ratio of the quietest individual source we would add into the data. So we specified an SNR threshold, and we varied this from something that was quite low, so minimum SNR of 5. And so you should then, what's left should be quite well described as a Gaussian background. And we also pushed it up to 50, where you have quite a lot of popcorn noise left over, and so it's not going to be as well described by a Gaussian background. So we controlled that. I was arguing earlier that the resolvability should be data-driven, so really we should have had this as a parameter that was fitted to the data, and then we'd find the choice at which our Gaussian background approximation was good enough. And we will certainly be exploring that in the future, but for illustrative purposes, we thought this was useful because you can see how things, your results get affected by making a bad choice of where you make this cut. Okay, so this is the result for two of the choices of SNR threshold, 10 and 50. The cross marks the true parameters. This is the amplitude of the individual sources and the slope of the background. With the lower SNR threshold, we're getting the right answer, but we see clear biases for the higher SNR threshold. And this is, again, because your approximation that the background that you're leaving behind is Gaussian starts to break down. So one would hope that if ρ was a free parameter, you would disfavor this higher value because it's not a good description of what's there. Okay, so we also identify the individual sources, and as expected, we find the brighter ones with a high SNR threshold and the less bright ones as we lower that threshold. Okay, so I have only a minute left, but I wanted to make a few final remarks. The formalism we've described here doesn't look very much like what is done in the context of ground-based detectors, where you have selection of data and correct for that in the analysis. But you can actually show that if you make the approximation that the LISA data is LIGO-like, so you have rare sources that are well separated in a long data set, you can actually recover the LIGO-like formalism from this one. And so the results are consistent in a regime in which they both apply. Another comment is that we're always somewhere making a choice about this resolvability threshold. So the other approaches I mentioned, Alex Criswell's and Heebie-Jeebie, they are making a particular choice of how the background is separated into resolved and foreground sources. And so there's either explicit or implicitly a choice of this resolvability function that's being made there, which we should aim to characterize, because that's what you then need to reweight to other populations. And the final comment is all of this assumes that we've done our reversible jump correctly, so we have a full posterior on all of the sources and the unknown number. In practice, we're not necessarily going to be able to do that for all source types. Things like extreme mass ratio inspirals and stellar origin black holes have a very big parameter space, and so almost certainly we will do a search which will be less sensitive first, and only things we find in the search will be added into the reversible jump. And so there's an extra selection that goes on there, but you should be able to fold it into the same formalism, because that then determines this alpha is what comes out of the search, and then the same interpretation after that. Okay, I'm out of time, so thank you.
Sorry, this will be really quick. Sorry, I just heard from one of the slides you said that it's difficult to know the noise of LISA, and so that got me a little confused, because aren't there places in the antenna pattern that are close to null, or Sagnac-like signals that will give you close to the noise, and can't you use that as like a prior?
Yeah, I mean, we are still fitting a noise model. So the Sagnac channel is insensitive to gravitational-wave signals. That doesn't mean it tells you anything about the noise. So it was realized, in fact, so the instrumental noise. So Sagnac is only noise, but the problem is that the noise that dominates the Sagnac channel at low frequency, where it's insensitive to signals, is not the bit that dominates the A and E channels. So you can't actually determine the right bit of the noise in this usual model where we have optical plus acceleration noise. And so there's still a problem that, I mean, it's all intrinsic to what we're fitting. We use the fact that we have 3 channels, and in principle, if there is information that's coming from certain combinations, then that is folded in. And so it's not that we have no means to separate noise from signal, but it's not as simple as saying this segment of data has nothing in it, and its noise is completely representative of the noise in this signal that's right next to it.
Thanks, John. Maybe my question is similar. I'm actually not sure. So one thing that I'm worried about in this sort of various population schemas is actually the role of the instrumental noise and how much that determines this all coming together. And one remarkable difference compared to ground-based detectors is that we won't have quiet parts of the data. So maybe what are your thoughts on that?
Yeah, I mean, I think in terms of how we're going to do the population inference, it's folded in because we will be fitting instrumental noise along with our galactic binary model and our other astrophysical foreground models. But there's going to be some degeneracy there. And so when you come to do this reweighting, you may be in a situation where you can only place an upper limit on the amount of noise that is due to the massive black hole population, because we've poorly constrained the instrumental component. But it should be all folded into the correlations between the pieces that we're fitting in the global fit. And the question is how well we can undo that afterwards. Do more work, alas.
Okay, let's thank John again. Our next speaker is Alexander Dittmann. Go ahead.
Great. Well, hello, everyone. If we have not yet met, I'm Alex. I'm a postdoc at the Institute for Advanced Study. And today I'd like to share with you some updates on trying to extract a little bit more information from GRMHD simulations of accretion onto black hole binaries. And since we've already seen way too many strain versus frequency diagrams, and we've had a number of lovely plenary talks by Krista, John, and our esteemed chair, I'm going to jump right into it. So I think, there we go. So I think there are generally two camps of efforts in theoretical pursuit of this problem. There's a huge parameter space to survey for accretion flows onto black hole binaries. And one area of research that we've had, I think, at least 6 talks on in earlier sessions is on trying to simulate as much physics as you can squeeze into a computer, right? So solving Einstein's field equations, the equations of general relativistic magnetohydrodynamics, and especially Vishal's recent work, actually coupling sort of a first principles Boltzmann-based radiation solver to the magnetohydrodynamic accretion flow. And so this is amazing. It's almost all the physics we think should be there, but it's also expensive and you can't really survey parameter space. The other, I think, large camp is to abstract or integrate away some of this physics to get a simplified system. So typically vertically integrating the fluid equations instead of having magnetic fields, people will use a sort of ad hoc viscous stress tensor to mimic some of the mass and angular momentum transport that we expect from magnetohydrodynamic turbulence. And this does still capture things like the time-varying gravitational potential of the binary, which is responsible for a lot of the interaction with the larger accretion flow. And by eye, radiation, turbulence, it's a little fuzzy, but lots of these features are the same. And because so much physics has been abstracted or integrated away, it's possible to do large surveys of simulations to understand how things like EM counterpart prospects or orbital evolution depend on binary mass ratio, eccentricity, disk parameters like disk thickness, effective stresses and strains. And so here are just some examples surveying disk thickness and eccentricity in the top panels and disk thickness and mass ratio in the bottom, looking at orbital evolution. So if the mass, in one mass e-folding timescale, how many e-foldings or shrinkings do you get in semi-major axis? And for thinner and thinner disks, you can get, over the course of a in-spiral in the LISA band, a decent fraction of a radian change in the phase due to gas interactions. So while it's not super important right at merger, it can be important for high signal-to-noise ratio signals. I should say there's also this work Michael discussed, some of his work adding post-Newtonian effects in this sort of regime, and Mudwit's also done work along these lines. So this is all well and good. Of course, I've done way too much of this, but there are serious uncertainties underpinning all of this that we've tossed out a lot of physics to do these sorts of suites of simulations, so it's uncertain how much of this actually carries over and can be trusted. And so there have been a few works, especially recently, trying to bridge this gap. Scott had a great paper a few years ago, not just surveying a few different binary mass ratios and magnetic field initial conditions, but actually calculating angular momentum fluxes through the accretion disk, which you can relate to the orbital evolution of the binaries. I think qualitatively it's fair to say that they agree fairly well with the vanilla hydra results, but there are, of course, differences from the MHD effects. And then recently on the Newtonian side, people have started to carry out large 3D magnetohydrodynamic simulations resolving accretion onto the binary, finding that angular momentum transport by MHD wind can affect the binary in spiral. And so this is the direction that I've been moving with some of this work. So we've been trying to set up binary black hole accretion simulations in Athena K. And by we, I mean really the majority of the work has been done, definitely all the hard parts, by Henry Zhu, who's a fantastic grad student at Princeton. People from Vacuum and R probably already know his work, but he's made huge contributions to all of this. It's really impressive stuff. So Athena K is a port of the Athena++ sort of adaptive mesh refinement and fluid modules to use the Cocos library, which just allows it to compile and run on CPU, GPU, ARM, whatever you have access to. And it has some physics capabilities that are really essential for this work. So it has a GRMHD solver for dynamical spacetimes. We haven't implemented it yet, or we haven't used it yet for this project, but a finite difference-based Einstein field equation solver. And instead, what we've been using is an implementation of this analytical, approximate, boosted, and superimposed Kerr-Schild spacetime advocated for by Luciano and Sean. In addition to that, we've implemented a bunch of sort of energy momentum transfer diagnostics to try and understand how the fluid exchanges energy and momentum with the spacetime and the binary. Now, just to describe the simulations in a little more detail, we are trying to leverage the adaptive mesh capabilities in this code to run these simulations for very long time scales. So to start out, we just barely marginally resolve the flow of gas plasma around the black hole horizons. And that allows us to take larger time steps and to allow turbulence to develop through the accretion disk out to very large radii. So we can simulate this for hundreds of binary orbital periods, so say 400 or so. And just as a proof, and then after it's developed and the disk has become eccentric, then we can add adaptive mesh refinement around the horizons to really resolve the flow of plasma around the ergo region and see jet launching and things like that. As a proof of concept, we're just running these at a sort of arbitrarily fixed separation of 25 gravitational radii. So this isn't especially physical, right? Over hundreds of orbits, they should be inspiraling, but to try and make more connection with sort of the Newtonian regime where torques are better characterized. We're just taking this approach for now, and then we can add inspirals later. And for now, we're also ignoring cooling. So this is going to be a radiatively inefficient accretion flow, not really applicable to most AGN. So just take that, just remember that when I show results later. And then just to explore what sort of accretion dynamics we can get here and the impact on orbital evolution, we're looking at two initial magnetic field configurations. In both cases, the magnetic fields are dynamically unimportant, very weak compared to even just gas pressure. But we're starting one set with just poloidal loops of magnetic field within the accretion disk, and another is being threaded just with vertical magnetic field lines, which is inspired by some recent simulations of accretion onto AGN from cosmological scales. So, dragging fields in from the interstellar medium. Now, unfortunately, our efforts in the add AMR and run at high resolution stage have been stymied by queues. So I have enough to show you a few orbits of videos for that, but most of the orbital evolution is coming from the much easier to run horizon unresolved simulation. So we expect the large scale dynamics to be captured here, but we only have a few orbits of actually the flow really within the ergosphere. Okay, so looking first at this loopy initial condition case, here we've restarted this with two different black hole spins, so just no spin and moderately spinning aligned. And in the top panel, looking at the density, okay, apart from the three-dimensionality, this is qualitatively pretty similar to everything we've seen from vertically integrated 2D viscous simulations, whatever. We see these streams of material accreting onto the binary from the cavity. We have this underdense cavity that's been opened up. All is well and good. There isn't too much difference in the density based on the black hole spins, at least in these cases. Now, if we look at the bottom panel, this is showing the just ratio of the gas pressure to the magnetic pressure. And in this case, we can see that, okay, throughout most of the disk, it is gas pressure dominated, but even in the non-spinning case, there are these magnetically driven outflows from the mini-disks. And of course, when the black holes are spinning, these outflows are much stronger as the flow can sap energy from the black hole spins. Now, looking at accretion rate and variability, we can measure the flux of material through the horizons of both black holes, take the total of that, that's fine. In the bottom panel, I'm showing the rate of angular momentum exchanged between the fluid and the binary, decomposed into the contribution to the orbital angular momentum of the binary, as well as the spins of each black hole. And so in this case, we were simulating non-spinning black holes for the initial stage, so they are spun up by accretion. And then in this case, the angular momentum contributed to the orbit should be enough to slow the binaries in spiral. In this, this case with this poloidal looped initial field configuration. Now, if we look at this periodogram of the accretion, total accretion rate, and the Poynting luminosity, there is a lot of variability, but very little on the orbital period, actually. So there's even more just high-frequency junk and low-frequency junk than your booming signal on the orbital period. Turning to this initial vertical field case, the dynamics are actually just in the density qualitatively different than we saw before and in any viscous hydro calculation. So the cavity is completely filled with these, this magnetic field configuration leads to very strong stresses that are able to rapidly fill the cavity with fluid. And instead, we do see some low density regions. Those are actually magnetic pressure supported flux ropes that are threading through the entire disk that can sort of buoyantly rise through the disk and are eventually disrupted by magnetic Rayleigh-Taylor instabilities. Then looking in the bottom panel, this field configuration, if you remember, say like a Blanford Payne setup, does lend itself towards more or stronger magnetically driven outflows. And so we can see that in both cases, there are more of these magnetic pressure dominated outflows, and of course they're stronger in the spinning case. Turning to torques and variability, it's more or less the same. Qualitatively, there's maybe a little bit of, the variability is on different frequencies. There's more high-frequency variability, maybe less prominent low-frequency variability. In this case, actually, the torque on the orbital angular momentum of the binary is actually a bit lower. And in at least the Newtonian definition of angular momentum, this case would actually inspiral a bit faster due to interaction with the accretion disk. And this is thanks to the winds driven off of the accretion disk, which sap energy and angular momentum from the system. So then the binary, of course, is interacting with sort of lower angular momentum material and can exchange more with the gas there. And with that, I'd like to leave you just with a few takeaways that these magnetic fields, depending on their configuration, can potentially accelerate binary inspirals and lead to very different accretion flows than we see in at least the viscous case or sort of standard poloidal loop conditions. So that needs to be looked into more. And binary periodicity, or periodicity on the orbital period, is certainly not universal. I haven't seen any LUMP. That is unfortunate. Although this actually, this lack of periodicity on the orbital period does agree with some sort of binary Bondi calculations people have done in this regime. So yeah, thank you.
Hey, that was a great talk. Really interesting stuff. I have two related questions. When you switch on the AMR levels, what kind of resolution are you getting at the horizons? And are you concerned at all that the outflows actually change when you turn up the AMR? And does that affect the wider disk?
Yeah, so actually, I forgot to point that out, but just... Okay. It doesn't want to play now. Okay, there we go. I mean, you can sort of see qualitatively, more so in this, well, even in this, at this scale, the large-scale disk doesn't look too different for the different spins, right? And qualitatively, you can see spin falls off at a few tens of RG in terms of its dynamical importance. Now, as far as the jet power, that does require a lot. So I think these are running at about 8 to 16 cells per horizon. And then to really get converged jet power, maybe we need to go up to one more level. So that's TBD. We need to check that before we actually publish anything.
Really interesting talk, thanks. I'm not worried about you not seeing the law. We have CVD simulations that are powered.
Yeah.
So you have the black holes for the 300 or 400 orbits? See that?
Yeah.
They're on the grid. Okay.
Yeah, it's on the grid, but then the horizon's barely resolved, and it's
The spins, I think you plot the spin evolutions.
Yes.
And they're decaying. Is that?
So the rate of change of the spin is decaying, but this is the
Hi, thanks for your talk. You mentioned Athena K can support GRMHD codes to run on GPUs. Do you have an idea of the speed up that you get running on GPUs over CPUs?
It really depends on the problem size. For GRMHD, I think there's enough work that it's usually pretty significant. I don't remember the numbers offhand, but if you look at, there's a table in the paper on Athena K that Jim led that just has 4 different GPUs, different node configurations, different solvers, what the speed up is. But it does very, very much depend on the system.
Okay, thanks. If the analysis has been done, I'll look it up. Thanks.
Very interesting talk. From Galactic simulations, what sort of we have been saying is that the fast nuclear events, the radiative efficient feedback, takes away the gas supply from the nuclear region on the lifetimes of 10 power 5 to 10 power 6 years. How do you think that would sort of affect your picture if you integrate that mechanism into here?
Frankly, I didn't catch your entire question, but the initial conditions, so here we do see that the initial conditions matter, and both initial conditions I've used are incredibly ad hoc, and I think a very interesting line of work that's been pursued a little bit, I think just so far in the Newtonian context, is taking at least sort of zoom-in cosmological style simulations and using that to initialize these sorts of simulations. And so that's work that I think was led by Minghao Guo and Haiyang Yang and Elias Most and Phil Hopkins have been involved in that sort of thing. And there have probably been other works that I'm not aware of as well, but that is an active area of research, trying to get realistic feeding initial conditions for these.
So if I understand your thoughts where you have the diagrams right, you effectively see everything but the orbital frequency?
Well, the orbital frequency is still there. It's just not as significant as others.
So how scared do we have to be about potential counterparts as identification?
So I'd like to go back to something I mentioned earlier, that we didn't include any cooling in the simulation. If we just look at the type of disks we get, right, this is incredibly thick, incredibly puffy. Physically, this corresponds to something like a radiatively inefficient accretion flow, like we might expect maybe to describe Sagittarius A star, which doesn't have much luminosity to speak of anyway. So I think it's actually not a big issue because these would not be very observable for other reasons. But in the super Eddington case, if these sorts of things carry over, that would be interesting and worrying.
Okay, I think we need to move on to the second speaker. And our next speaker is Anuj Kankani. Go ahead.
All right, hi everybody. In the spirit of this mid-session, this talk will be nothing like the last talk. My name is Anuj Kankani. I'm a final year grad student at West Virginia, and this is work I'm doing with my advisor, Brice Williams. So the kind of broad introduction topic. This is going to be a waveform modeling talk. So as we all know, binary black hole mergers roughly split into 3 parts. You have the in-spiral, the merger, and the ring down. I'm going to be talking specifically about how we model the merger and ring down part. So numerical relativity gives us the most accurate way, but of course it's really expensive. So we all come up with semi-analytical models. But for the merger ring down, most of these models are pretty reliant on numerical relativity. And while that can give you accuracy, it leaves you tied to the quantity and quality of your catalogs, and it doesn't give you a whole lot of physical insight into how the merger actually works. So one way we kind of work around that is with something called the backwards one body model, which broadly speaking is a analytical merger ring down model for the merger ring down radiation. And so the original derivation is based off how null geodesics get perturbed from the light ring of the remnant black hole. And if you follow the math, you get this amplitude, this hyperbolic secant, which I want you all to remember this because there's actually a lot of really interesting physics hidden in that deceptively simple hyperbolic secant. And then you can also get this analytical phase. Now, the really cool part about Bob is, unlike most merger ring down models, it is really minimally reliant on numerical relativity. In fact, you only have 4 parameters. Like every model, you have a final mass and final spin to define the remnant black hole in its QNMs. You have a peak amplitude for an overall normalization. And you have an initial frequency parameter that we find is actually very weakly dependent on the remnant properties. So while all this physics and minimal reliance is really nice, it's only useful if it's actually accurate. So for this talk, everything I'm going to be talking about is with the gravitational wave news. So that's the first time derivative of the string. And the reason I'm doing that is, as you show in the paper, if you look into the physics of what that's encoded in Bob, it's fundamentally describing the gravitational wave news. So this is just a mismatch plot between Bob for the news from the peak to 75 and afterwards, between Bob and EOB and surrogate-based models. And you can see Bob is already competitive with these state-of-the-art waveform models, but is able to do this while being minimally reliant on NR. And because it's minimally reliant on NR, when you go to kind of the corner areas of the parameter space where aren't that many waveforms yet, for example, systems with really high remnant spins where numerical relativity is more expensive and it's more difficult and it's also just a corner space, Bob is just as accurate here as it is everywhere else. For example, if you do a surrogate domain, a surrogate model, you'll have to extrapolate outside its training domain here, or an EOB merger ring down model, which is really NR reliant for this part of the waveform, starts to lose accuracy. But Bob here is just as accurate here as it is everywhere else. So we know Bob is accurate, but one of the really things that interest me is kind of understanding why Bob is so accurate. Because if you look at Bob's derivation with this light ring geodesic, it kind of brings these QNM analogies. And so I wanted to kind of investigate this link between Bob and quasi-normal modes. So for anyone who doesn't know, quasi-normal modes are kind of the characteristic complex frequencies that define the perturbed remnant black hole as it settles down into its final state. So for example, if you have the 2-2 post-merger signal, the 2-2 mode, you can describe it pretty well using a sum of quasi-normal modes. So the first obvious thing to do is, well, let's just do a sum of quasi-normal modes. Let's do Bob and see how they compare. So essentially on this plot, if you haven't seen it before, on the y-axis we have mismatch, which is just a measure of accuracy. Lower is better. And in the black, we have Bob. And in the colored lines, we just keep on adding more and more quasi-normal modes. So you'll see qualitatively, Bob is kind of acting like a quasi-normal mode in that it has its turn off, even though it acts a little bit better before the peak. But if you look around the vertical line where the peak is, you're seeing Bob is able to match the accuracy of around 4 to 5 quasi-normal modes. Now, this is really cool because normally quasi-normal modes, in addition to the final mass and final spin, they also come with this complex coefficient in front of each QNM that we don't know beforehand. So normally we take some numerical relativity data, we take some QNM model with 4, 5, 6, however many QNMs you want, and we perform a least squares fit and we obtain those coefficients. So a 4 or 5 QNM model, for example, might require 10 or 12 free parameters, whereas Bob is achieving that level of accuracy with only 4. And if you remember that hyperbolic secant amplitude profile I asked you to remember at the beginning, if you write that out as a series, like I did in the bottom there, if you're familiar with QNMs, you might notice that each term, that damping time is just the damping time of higher overtones in the iconal limit. So you can see how Bob is kind of incorporating all of this QNM information. And in fact, in a recent paper, we show for the Posh-Teller potential in how, from a good approximation, you can actually recover the hyperbolic secant by considering all of the QNM poles, specifically for the gravitational wave news. And in addition to the alternating sign, which is kind of like alternating phase structure, if you change the sign -1 to e to the I pi, you'll notice if we consider really late time, so when t is much greater than t peak, all of these higher order terms kind of become negligible, and we're left with only the first term, which kind of just looks like a quasi-normal mode. Now, it was pointed out a couple of years ago for a superkit case that this allows you to put a link between the peak amplitude of the news and the fundamental quasi-normal mode. So this is something that Bob is predicting. And so this A220 on the left-hand side, that's something we normally obtain by doing a least squares fit to a numerical relativity waveform. But Bob is saying we have this inherent link between the peak amplitude and this usually fitted for quantity. And we compared it to a bunch of NRCCE waveforms, and we found it's extremely accurate, basically to within the inherent fitting errors of the surrogate model itself. So while this is all very cool, if you notice around 2 slides ago, I pointed out very quickly that Bob seems to be kind of turning off slightly better than the QNMs around the peak. And in general, it has really, really good performance at the peak, while not requiring a whole lot of NR information. Now, that's kind of strange, because the peak is usually associated with the merger, which is when you need the most NR information. And so one of the ways we discovered why Bob is so accurate is something to do with direct waves. So this is a more recent development. It was recently found by Shida et al. That they designed, designed frequency domain filters that specifically target the QNM content of the waveform. So by applying it to numerical relativity, you can essentially remove the QNM content from the merger ring down radiation. And so what they did by doing that was they identified a really specific non-QNM part of the merger radiation called the direct wave. And so what we did was, well, let's apply this filter to Bob as well and see what we get. And what we discovered was that Bob was already modeling the direct wave really accurately. So here is the classic GW150914 example, 0305, and then you have even high spin, low spin, high mass ratio. Bob is doing astonishingly good job of modeling this merger non-QNM part of the radiation, which helps explain why it's so accurate around the peak. It's capturing all of this QNM information, and it's capturing this non-QNM information. So how can we use this? Well, in addition to improving the modeling, how can we use it to understand the physics? Well, this direct wave has been associated with the horizon properties of the remnant. So it's been argued that the direct wave frequency should be close to the horizon frequency of the remnant. And we can then use the horizon frequency of the remnant to do things like test Hawking's area law and do all of these cool tests of GR. What we found was when we applied this rational filter across the SSS catalog, so the horizon frequency is in the red there, and if we find kind of the average, median, the direct wave, what the direct wave frequency is near, it doesn't really correlate with the horizon frequency at all. But you'll notice the red line and the black and pink line all kind of cross at one spin, around 0.7 final spin. Now, this is really interesting because in the cases that have linked the direct wave frequency to the horizon wave frequency, so for example, 0305 here, which is the 150914 like case, or GW250114, which have done Hawking area laws, they all have the final spin exactly at that crossing point. So what they see as, the direct wave frequency they recover is close to the horizon frequency, but it's just a coincidence. It's not the actual physical result. Therefore, if you do things like Hawking's area law and try to interpret physics from this, you may get what appears like a violation of GR, but it's really not. It's just not the right physics. And there will hopefully be a paper submitted by us on that very soon. So I'll leave you all with this. Essentially, Bob, very cool analytical merger ring-down waveform, minimal NR reliance. There's an incredible amount of interesting correlations with QNMs that I only scratched the surface of here. And Bob is able to model a direct wave, and there's a whole lot of future stuff you can do with Bob that's super interesting as well. Thank you.
Just like to ask you to explain, there were several curves in the plot where you were claiming that Bob models very well the direct wave. Can you explain all the different curves?
Yes. So the black is, we take the SXS waveform, apply the rational filter. So that's the NR direct wave component. So the pink line is where we apply the exact same filter to Bob as well. The blue line is, we did something slightly different, is if you notice, in the hyperbolic secant, the QNM information is incorporated through the iconal limit, right? It's 3 over tau, 5 over tau. So for the damping times, for the overtones we use in the filter, we use the iconal limit. And some cases one works better, some cases the other works better. I'm not exactly sure what the correlation is there, but overall they both work pretty well.
So I had to understand that the three agreed between about minus 10M and 10M.
Yeah, there's usually 10, 15M agreement around it.
Hey, nice talk. So if I want to do like a no-hair theorem test with this model and the QNMs that you get out with the amplitudes, is there a way to allow the frequencies of damping times of each QNM to deviate from curve?
Yes. So this is really one of the advantages of Bob, is really so if you see that tau, that's just the damping time of the QNM. So you can easily just add some phenomenological parameters, say some deviation. Same omega, I don't have the explicit form of omega here, but similarly it's just the QNM quantities that go into it. So you can just add some like deviation parameters.
You just allow those to like be sampled over and P. Okay, thank you.
Hi, thanks a lot for the nice talk. I was wondering whether you could explain a bit more about the connection between the model and the statement that it's connected to the news.
Yeah.
How do you know that, and is it connected to balance laws in some way?
Yeah, so there's actually a couple of different ways. So empirically, we can show mismatch is most accurate. Also empirically, we can show that this relationship is most accurate for the news. But the real analytical, physical understanding is, if you're familiar with the Posh-Teller potential, you can show that all the QNM poles, you can resum them for the gravitational wave news to the hyperbolic secant. So specifically for the news, you can recover the hyperbolic secant.
Okay, let's take it at the beginning. And our next speaker is Julie Comerford.
Thank you. There are fewer equations in my talk. Definitely no hyperbolic secants. So I'll be speaking about using observations of galaxies and their massive black holes to build the best models that we can of the gravitational waves that LISA will observe. Okay, so observationally we do this by starting with pairs of galaxies that we expect to merge, populating them with black holes, and then using timescales to follow them all the way through and produce a binary black hole merger rate for LISA. And so if I kind of break this down into its simplistic parts, we need to measure a galaxy merger rate, which provides the initial number density of the binary black holes. We need to populate those merging galaxies with black holes of certain masses. which provides the amplitude of the gravitational wave signal from a given binary. And then we need to know the amount of time it takes for those binaries to evolve from larger kiloparsec separations down to sub-milliparsecs, where they strongly emit gravitational waves. And so our goal is to measure each of these with observations whenever we can and do it as well as we can. And so Joe Simon and I published a paper in December where we have a new measurement of the galaxy merger rate. And then we combined those observations with the pulsar timing array measurements of the gravitational wave background and use that to set some constraints on the binary evolution timescale. I will be talking about neither of those things. Today I will be focused on that middle piece, the masses of the black holes. And so if you have low redshift galaxies, you can use dynamics around the black holes, get accurate mass measurements. But beyond the local universe and at the redshifts that we care about for LISA, we can't do dynamical mass measurements. Instead, we need to lean on scaling relations between the mass of a black hole and its host galaxy properties. And so the most commonly used scaling relations are m sigma and mm bulge. And my graduate student, Maggie Huber, who is here, has done work on comparing these two scaling relations, and they have found that the resultant gravitational wave signal that you get depends very much on which scaling relation you use to get the black hole masses. So for more information on that, then after this session, you can see Maggie's poster or take a look at their recent paper. Okay, so currently the way the models work is we have a galaxy merger. We use one of those scaling relations to plop down a black hole at the center of each galaxy and give it some mass. And then what we do is we say, okay, we've set the masses of those black holes in that galaxy pair. Then nothing happens. And then those same mass black holes eventually merge and create gravitational waves. Now, of course, the problem with this is that's not the way black holes work at all. At all. We know this is wrong. So let's erase the board and start over again and take a look at how galaxies actually evolve in mass throughout the course of a galaxy merger. So first, at the early stages of the merger, when the black holes are separated by kiloparsec scales, we know that the merger is driving gravitational torques of gas towards the center of the galaxy that fuel the black holes and grow their mass. And then as those black hole pairs evolve down to sub-parsec separations, we saw from Alexander's talk earlier in the session that a circumbinary gas disk forms around those binaries and that the binaries can accrete and grow in mass from that circumbinary gas disk as well. So let's focus on trying to measure the effects of these two forms of black hole mass growth as the black holes progress through their merger. So I'm going to start with the large-scale kiloparsec scale separations, where we've got the galaxies driving gas onto the black holes. So in order to study this observationally, we built a sample of galaxy pairs in Sloan, and we required that at least one of the galaxies host a broadline AGN. We looked for cases of 2 broadline AGN. We didn't find any. So all 76 of these pairs, think of like one of the galaxies has a broadline AGN. And why do we want a broadline AGN? It's for that tricky mass bit. If you have a broadline AGN, then you have an independent way of measuring the black hole mass where you don't have to use those scaling relations. So we use the single epoch virial method on the broadlines to get an independent measure of the black hole mass. So we use that black hole mass measurement and the bolometric luminosity AGN to get an accretion rate, a growth rate on the black hole. And so we did this for the sample of galaxy pairs, and so now we want to subdivide it and say, oh, is there anything interesting going on here? Are the accretion rates different for black holes in a major merger versus a minor merger, or whether the black holes in the more massive primary galaxy or the less massive secondary galaxy? So here are the results broken down by all the different types of galaxy mergers that we have. So on the y-axis, we have the excess Eddington ratio compared to what you would get for an AGN in a non-merger. That's what that like dashed horizontal line is accretion rates of AGN in non-mergers. And so you can see that the entire merger population has a higher accretion rate than the AGNs in non-merger by about 35% higher. And then we break it down by minor merger versus major merger. Is the black hole in the primary or secondary? Or is the black hole overmassive or undermassive compared to what you would get if you use bulge to get the black hole mass? And so what we find is overall higher accretion rates if you're in a major merger, if you're in a secondary galaxy, and if you're a black hole that's undermassive relative to what bulge says that you would be. Okay, so those are accretion rates. I'm going to turn that into some amount of mass growth for the black holes. So in order to do that, I need to multiply by a time scale. So for the time scales, I turn to the simulations papers. They all say that these accretion events in galaxy mergers last twiddle 100 megayears. So I'm going to take 100 megayears and multiply that by my accretion rate. And I find that the median black hole in my mergers grows in mass by about 20% from this accretion event. And since we found from the previous plot that we have higher accretion rates for the black holes in the secondary, less massive galaxy, that means that we're also driving up the mass ratio of the black holes. So the median mass ratio also goes up by about 10% during an accretion event. And I want to emphasize this is for one accretion event during the course of a merger. If you look at the simulations papers, they can show there's multiple accretion events happening before the black holes actually coalesce. So this is kind of like a lower limit on how much mass growth is actually happening during a galaxy merger. Okay, so we've talked about the kiloparsec scale phase, black hole mass growth, median value of 20%. Now let's focus in on that subparsec separation where you get a circumbinary gas disk. Now, simulations have shown that for black hole binaries embedded in a circumbinary gas disk, the secondary, less massive black hole is the one that usually accretes more, although Michael's talk from 2 days ago showed that that's not always the case, so it's a little trickier than what I'm showing here. But when the secondary black hole is accreting more, because it's closer to the edge of the disk there, that's called preferential accretion. Preferential accretion onto the secondary, and that has the effect of increasing that Q black hole, increasing the black hole mass ratio, and making it closer to 1 as well. So let's see exactly how much those black holes grow in mass during this subparsec accretion phase. Now, for that, I like to do things that are observationally motivated. As we heard from Maria's talk, there's a lot of work going into finding binaries, but we definitely haven't measured like accretion rates onto binary black holes, so I don't have any observations to go off of. So let's just say that the black holes are going to grow by maybe 10% or 20% during this phase, and let's just see what happens. And so that's what this plot shows, is how the black hole mass ratio changes from assuming there's no accretion happening at all, that's the black line. So this is starting from a sample of our pair galaxies of mass ratios 10 to 1 to 1 to 1, populating the black holes, allowing no further black hole mass accretion. You get that black line, and you can see that most of the mergers result in minor mergers of black holes. So that dotted line is a dividing line between minor mergers on the left and major mergers on the right. But if you allow the black holes to grow by 10% from the circumbinary gas disk or 20% in orange, you can see how the black hole mass ratio pushes towards more major mergers. So in the 20% case, most of your mergers now result in major mergers of black holes, whereas with no growth at all, most of your galaxy mergers result in minor mergers of black holes. So this can become a significant effect pretty quickly. Okay, we also showed in this paper that if you take these results, build the model, and compare it to the gravitational wave background that was measured by pulsar timing arrays, we heard from Laura Blecka's talk that there's this problem of the gravitational wave background being larger than what we expected from the models. And if you just have the model with no black hole mass growth, then you get the probability distribution function shown in black. And you can see the problem. Oh my God, it's way too low and the measurement is way too high. But as soon as you add just 10% or 20% of accretion mass growth from the circumbinary gas disk, it solves the problem. The problem goes away and everything lines up. And this effect of preferential accretion should be even stronger for LISA sources, since they're at higher redshifts, where galaxies are more gas-rich, there might be higher accretion rates, and so this should be a big effect for galaxy mass growth at LISA redshifts, even more than at the lower redshifts that we probe with the pulsar timing arrays. So we looked at black hole mass growth through different phases of the galaxy merger, from kiloparsec scale gas inflows to the very small circumbinary gas disk phase. And we found that the mass growth that happens there increases not only the masses of the black holes, but also increases the mass ratio of the black holes. And so that means that the chirp mass increases, and that means that the gravitational wave strain from any given binary also increases. So all of this means that we should get stronger gravitational waves from binary black holes that LISA will detect. And so my main takeaway is, as you're building models of black hole binaries, you need to include the mass growth that happens during the galaxy merger, and it has the, well, happy effect that it makes the gravitational waves stronger for LISA. Thank you.
Thank you very much. This is an excellent idea. With respect to PTA, though, as a check, the majority of the background is probably from extra massive black holes for the pulsar timing arrays, like 10 to the 9 solar masses and above. I had the impression that those tended to be associated with ellipticals, or relatively gas-poor galaxies. Any thoughts on that?
Yeah, so this is, and I've been asking people at this conference, and I haven't gotten like the answer yet. So if you know the answer, tell me. But like, how often do galaxies actually have circumbinary gas disk at the binary phase? And does it depend on morphology and how much gas is available? I would love to know that, to put that as an input to the model, because right now we just kind of did like back of the envelope. Let's assume they all have a circumbinary gas disk and they're growing by 10% or 20%. And so there's a lot more refinement we want to do to the model to make it more accurate. And that's what I'm hoping to learn here as well.
About a 20 to 30% increase in the mass during merger episodes. That number seems to be in tension with the Zoltan's argument, so you don't get that much of a growth from gas accretion, which we expect to be much more.
Yeah, so your question is?
My question is that you're not accreting any, I mean, 20% mass increase in a galaxy merger is insignificant.
20% mass growth?
Yeah, 20 to 30%, like these numbers that you do. So maybe you're underestimating the growth.
Oh, I definitely think I'm underestimating the growth.
By perhaps orders of magnitude.
Yeah.
So.
Yes, this is, yes. There are more steps to come to try to make this more observationally accurate. This is what Maggie's going to do next for their thesis. So stay tuned.
Great talk. So you showed the result for the Sloan galaxies where the secondary there is like a excess AGN. Can you explain why that's the case, and also how do you think this result will change at high redshift compared to like the low redshift?
Yeah, it's so cool that the secondary black hole is the one that grows the most. And it's because of the mass difference between the two galaxies. The more massive galaxy has a stronger gravity and like really messes up the low mass galaxy, whereas the low mass galaxy is wimpy and barely does anything to the high mass galaxy. So that's why the big galaxy like triggers all the gas inflows onto the black hole in the smaller galaxy. Yeah, so that was the strongest effect we saw, was the highest accretion rates in black holes in the secondary galaxy in minor mergers, where the mass difference is the greatest between the two galaxies.
Thanks for the talk. Quick question. So with the secondary preferential accretion, once you get to the circumbinary disk, how sensitive is that to the mass ratio when it enters that regime?
Yeah, so that's, we used an analytic expression from the Paul Duffel's paper, and so that takes it as an input, like what's your starting mass ratio, and then here's what the ending mass ratio will be based on our simulations. So we use that analytic expression, and that's how we propelled it forward. So I can point you to where that is in their paper.
Okay, let's thank Julie again. The last talk is by Maria Babiuc.
Okay, so I know that I had to adjust the title. So it's not compact binaries, but I need to fit in this section. So no worries, I meant to talk about this anyway. So those are my undergraduate students with whom I did work. I'm starting with the most popular plot in this conference. This time we focus on massive black hole binaries, and look how beautiful the signal is the loudest that LISA can resolve. The problem is that it's not the detection, as you learned yesterday, is the inference of the science. So at that signal, the waveform systematics can dominate the error budget. So what is to be done? There are open questions. The first one to ask is, do we have the right simulations? And that needs to be informed by population studies. The second is, how accurate is accurate enough? We don't want to work more, right? But we know that we have to work a bit more. So how accurate are numerical relativity codes now? I'm talking about numerical relativity codes because they are at the base, and they are the ones that inform the models. So for this, we take a 3-steps approach. We build a coverage map, a health check of numerical relativity simulations, and then a cross-catalog check, basically the mismatch. So we want to look at relevance, if we simulate what it should be detected, at difficulty, how difficult are those essential simulations of the waveforms, and at the accuracy. So is the physics that we want there? So again, that is the big question, and this is the roadmap. We build a coverage map in which basically we impose a matrix, and then a convergence test, and then the matches. Okay, so the first step is to clarify the parameter space. So what in the world is the parameter space? So we have the manifold of detection and the coordinates that link the models that we have, the intrinsics, with the detector. And the idea is that we will infer the science. So the science is are not independent, but if the intrinsic coordinates are not good, then the science inferred is not good. So how many do we have? Well, the basics ones are 7 for the quasi-circular and 7 for the extrinsic parameters. But then the fun begins, right? When you add eccentricity, precession, environment, memory, beyond your really exciting stuff. So let's look at what big numerical relativity catalogs have. And at the first look, this is quite encouraging. We have a lot of simulations in the low eccentricity and in the low spins and spreading all over. We have a lot of precessing. Several eccentric systems. We see SSX is with blue, RIT is with orange, but it starts to thin out towards higher mass ratios. So that is a little bit worrisome, but let's look at each catalog in part. This is SSX, again, a very dense population in the, it's weird how I can move that now. But then you can't hear me. All right. So again, we see that the mass ratio is spreading, but is very thin towards the relevant boundaries of the massive binaries. While the RIT, we have a lot of simulations with, again, aligned spin or equal mass ratios or small mass ratios, but it starts, the coverage starts thinning after the mass ratio smaller than 5. Looking even in more detail at the effective spin, precession, and eccentricity, we see that the eccentricity basically is very poorly populated. We can't talk about eccentric system at our level of precision if eccentricity is lower than 0.2. Unfortunately, so we have few eccentric systems. We have a lot of SSX processing, not that many in the RIT. Okay, so what is the idea with the coverage matrix? We want to see what systems are relevant, so demand, and what are stressful. So the matrix is built by the demand and stress. Now, the astrophysical weight is positive, so we use the same parameters, Q, spin, precession, as eccentricity, while the stress is also counting spin, mass ratio, precession, and eccentricity, but we want systems with high astrophysical relevance and low numerical spin. We try to decouple them by adding important numerical characteristics like number of orbits and levels, convergence, center of mass, and the bonus. If you simulate the same system, do you get identical waves? So because we have this coupling, the matrix doesn't reach. For example, if you want frontier and edge simulations, you penalize them so they can't be simple. And if you want control simulations, if they are fragile or demanding, they are not good to use. So there are, by design, some cells that are not populated. What is important for LISA science is this middle region, and we see that we have plenty of simulations in this middle region, which is good. We do see that we do have some dream simulations in here, but they do need to be carefully looked at and vetted. So now, those two catalogs simulate a lot of systems, and many of them are basically the same. So we want to see what is the mismatch between those waves for different catalogs. So in here, we match SSX and RIT, and we do want to specify that we cannot match on the effective spin, but we need to match on individual spins, because that is basically, we match on all 7 coordinates. Okay, so the next step is to establish if those waves are healthy. So the health check is developed as a rubric, and we give grades, we give medals, gold, silver, and bronze. Now, we weigh the convergence the most, but at this level, all codes are reporting convergence, right? So it's not that simple to go and analyze convergence for SSX, right? Luckily, we do have there is a new paper by the RIT group that released several levels of waveforms, so we were able to establish convergence. The red ones are the ones published by them, and the green and blue are the ones that we found. And we see in here that systems that are not eccentric are clean, but eccentric systems are not showing convergence or are overfit, so we call them fragile. So this is a comparison between RIT and SSX, and we establish both in the time domain the difference between the phase, and also calculate the mismatch the way Alvin explained yesterday. And this is the anatomy of a clean match. We have a line orbit spinning equal mass system, and the mismatch between SSX and RIT is 10 to the minus 4, so this presents the floor for the error between those two codes, so this is good. Now, the anatomy of a fragile match, this is for eccentricity. The eccentricity is already difficult to establish. We have our own eccentricity measurement because RIT, for example, has one eccentricity on the web and one eccentricity in the metadata. And we do not say that this is basically wrong, because when you fit in eccentricity, you need to be more careful. For example, codes don't report mean anomalies, so we do need to establish that as well. Now, 10 to the minus 4 is amazing, but is it good enough for LISA? So it's maybe if that black hole happens to be in this region and the SNR is only 100. So I'm going to end here with some gaps and priorities. Those are a working list, and we need to be informed to build that matrix. We really need to connect with the astro community, and this is the summary of my talk. Thank you.
Thank you, that was great, but how are you handling the difference in the waveform lengths? Like, are you, if you compare an SX waveform to an RIT waveform, and you put the weight as 10, but what does it mean?
This difference is simply difference in phase. So I'm building the continuum for the RIT and compare it with the highest resolution for the SSX, and just subtract the phases.
Right, but if SXX had 30 orbits and RIT had 10,
we fit everything. Yeah, we fit everything at the merger. Yeah, so this is the next step we'll fit in the beginning because it is essential for the eccentric systems. We realized that another reason why maybe is because we didn't fit within a domain in the beginning, but right now we just fit everything at the merger.
Okay, are there any more questions?